All right, hi everyone. Um, Thanks for joining me once again. Sorry, I got some technical difficulties running around. I forgot my iPad at home, but hopefully we should be okay. All right, so the function f and g are differentiable. Great, thank you. For all x, f of g is equal to x, okay? And g of f is equal to x. So the idea here is whenever you see stuff like this is what we call inverses. They cancel each other. Example, if I say a square root of x squared, this becomes x, right? The square and the square root cancel out. So this is the idea in general what we're talking about. So if f of 3 is 8, okay, f of 3 is 8, and f prime of 3 is 9, what are the values of g of 8 and g prime of 8, okay? So we had a thing about this before, about inverses, like the derivative of inverse functions. Do you guys remember this? Um, and the idea is if I give you a graph, let's see, this is the graph going this way, and the graph, oh my goodness, it did crash, come on. And then the inverse graph would be something like going this way, that the slopes of the points would be just the reciprocal. You guys want to remember that? It was like f, uh, it was like the derivative of the inverse of x is equal to 1 over f prime of y or something like this. Do you guys remember this rule-ish? Okay, and the idea is that I don't remember what the rule is all of a sudden, so I'm glitching out. But it was just like the reciprocal, okay? Now, if I give you an example, let's see if we can think of another way of looking at it. Okay, so our point is that we're given a point here that 3 becomes 8 and 8 becomes 3. That's what the inverse does. So the g of 8 is the inverse, the backwards operation. So this actually becomes 3, right? This answer here is 3 because of the inverses of each other. So what is the derivative of 8? And that's the reciprocal of 1 over 9, I think. Let's double check this. So I ran out of space here, darn it. So if these are inverses of each other, so we're actually looking at the derivative of it at 3. Okay? And then it was written in a way of, it was like f prime of f inverse of x or something like that. Okay? Which was like 1 over, in this case, what's the derivative of the inverse? It's going to be 9. So they actually tell us right here on the left-hand side, you can see that that says g of 8 is 3, which is our inverse operation. And then the derivative of our inverse is really 1 over the derivative of our original function, which is, in this case, is 1 over the derivative f prime of 3 in this case. Okay. Do you remember that rule? Yeah, that was pretty much the rule. So whenever you have a problem when it comes to whenever it comes to inverse, is that whatever graph you have, as I mentioned before, if that's this, let's say this is your f of x graph, and then this is your inverse f inverse graph, right? They undo each other. Okay. Example is this is x squared. If you say this is x squared, and this is the square root of x. Come on. They undo each other. And the way we find the derivatives is that they're actually really similar to each other. They're actually the same thing except they're just the reciprocal. Now, how do you know it's a reciprocal and not just a negative reciprocal? We always say negative reciprocal. I want you to just look at these two slopes here. They're both positive, aren't they? So the big deal is that if I take the derivative of this guy over here, that's going to be 2x. The derivative of this is 1 over 2 squared of x, right? And if I plug in numbers, let's say if I plug in a number for like 1 here, I would plug in a number for 1 here. If I say x is 1, for this problem, for this graph, x squared would be 1 comma 1, right? That's x squared. So going forward and backwards is exactly the same. But if I say 1 comma 2, no, 2 comma 4, 2 comma 4, right? 2 squared is 4. Going backwards, 4 comma 2 going backwards. So over here would be like 4 comma 2. What's the slope? And are they related? If I plug in 4 here, that'll be 1 over 2 times 2, which is 1/4. But if I plug in 2 here, that would become 4, right? So the slopes are actually related. It's just that it's 1 over the original derivative. We had gone over that before. And again, the formula is it's something you have to kind of remember, but it's like, the derivative of the inverse function, x, is equal to 1 over the original derivative of y. Yeah. Okay. Or vice versa. If you put x in, that's y, and y in the next. All right, good question. That's one of the things that we just had to go back and memorize. And there's actually no calculator needed on this one. Okay. Of course, you know that'd be nice to me. Let's look at 12. So I'm working on the Windows system, so it's taking me a little longer. Okay, here's number 12. Let f be a differentiable function such that f of 1 is equal to pi. Okay, and then f prime is that. What is the value of f at 5? So we have to go backwards on this. And so we know we're taking the integral. And if we just set up this integral of the square root of x cubed plus 6, okay, dx. And then once we take the integral of that, we have to find what the value of 5 is. Now, there is a way of doing this, right? If we just plug in instead. So let me give you guys a graph. Let's say this is some graph. Let's just talk about some graph. And we're given from 1 to 5, okay? If I take the integral of this, it goes backwards, okay? Oh my gosh. If I take the integral of this, let's say from 1 to 5, what does that give us? That gives us the cumulative change from 1 to 5, okay? And so that gives us the area between 1 and 5 on my original graph. Now, what is the value of f at 5? Well, what is, in the original graph, what is the value of f at 5? Well, isn't that just f of 1 plus the integral between 1 and 5 of f of x, f prime of x? I'm saying this in a slightly different way. Is because if I forget and I have no clue what's going on, I have to really go back to the basics. And in this problem, it's not a problem which I can do by hand because of this right here. If I try to think and I try to make it u substitution, if u is x cubed, I can't take the integral of x cubed. Well, if I take the derivative of x cubed is x squared, but there's no x squared to divide out. So since this is a calculator problem, I need to use my calculator for it. Now, I can't just stick an x here because the calculator won't do that problem for me. So I'm stuck with trying to figure out how can I use my calculator as a tool. Now, the way I thought of this problem is, okay, first, if I had to take the integral between 1 and 5, that's just the area of this curve, right? That's my cumulative change. Come on. That's my cumulative change. right? So that doesn't tell me what my value at the end is. It just tells me how much I changed from f of 1 to f of 5. So f of 1 they told me was pi. If I add my cumulative change to it from my calculator, that gives us my final answer, f of 5. Okay, it's like I know how much I made at 1 o'clock. I know how much I made between 1 to 5 o'clock. I just need to add those values together. So if I go ahead and plug in my calculator, you guys can plug this into your graphing calculator. I'm sorry, it's too hard for me to switch right now, but you guys can type this in your graphing calculator right now. The integral, we're gonna take this integral from 1 to 5 right here, because that's really the only thing we could have done with this problem. Now, how can I use that to help me solve the problem? Okay, I'm gonna use my Web EMU. So math 9, oh shoot, math 9 from 1 to 5 of the square root, second square root of x cubed plus 6 dx. Okay, the calculator is telling me this is 24.671. I'm going to add pi to that. We end up with 27.81, which is our last answer, 814. Okay, 13 looks like a similar question. They give us very simply, they told us, okay, here's the derivative, here's the rate of change, is square root of 1 plus 2x cubed. They gave us from 2 is 0.04, and they want what happens at 5. So looking at a simple graph, here's 2, here's 5. They gave us some type of square root graph, whatever it may be, and they want us to find out what is the f of 5. Okay, well, f of 2, they told us was 0.4. We're going to add our change to get to 5. Well, the change is just the integral, the cumulative change. This is f prime of x. So integral from 2 to 5 of the square root of 1 plus 2x cubed dx. Plug that in a calculator, and then add that to 0.4. So let's go ahead and do that. So 0.4 plus my change, math 9, from 2 to 5 of the square root of 1 plus 2x cubed and x. And we're looking at 20, this is 28.605. Adding 0.4 to that is going to be 29.005. Okay, you guys feeling okay about those two? Feeling a little bit better? Okay. All right. Okay, so here's number 19. For t is greater than 0, h is a differentiable function of t that gives the temperature in degrees Celsius at an Arctic weather station. Which of the following has the best interpretation of f? So h prime at 24. Okay, let me read this again because there's a lot of words. T, okay, for t hours, okay, so t is greater than 0. So after 0, we're talking about hours. H is a differentiable function that of T that gives a temperature in degrees Celsius. Okay, so H itself we know is just temperature. Okay, H is temperature. Oh my goodness. H is temp. So H at 1 would be some type of something degrees Celsius. Okay, which of the part be the best to describe H prime? Well, if we're saying H prime is H of T, right? If I take the derivative, wouldn't that be dH over dt, right? So this is time. And this is, oh my gosh. And this is, up here, is temperature. So this is change in temperature over change in time. Okay, so h prime of t is our change in temperature and change in time. At specifically at 24 hours, this is the change in temperature, the rate that temperature is changing in relationship to time at the hour of the 24. Okay, so let's say the first one, a change in temperature during the first day. Nope, this is, though it's 24 hours, this is just the rate of temperature at this one point. Okay, the change in temperature during the 24th hour, that looks like the answer, B1. The average rate, this is not the equation for average derivative. Here is the exact value, the instantaneous rate. The rate at which the temperature is changing during the first day, nope. The rate at which temperature is changing at the end of 24 hours. At the end of 24 hours? It's not at the end of the 24th hour, just at the 24th hour. The change in temperature during the 24th hour. The rate of change, so it's either the first one or the last one. The rate of change, the change in temperature, the rate at which temperature is changing at the end of the 24th hour. Why does it say at the end of the 24th hour? These words, I hate words, but it's either the change of temperature at the 20. I feel like it's the second one, but the last one's so wordy, and it tries to, it's like tricking me. Let me check. The rate at which the temperature is changing, the change in temperature, the rate we had talked about. Okay, so because it's based on time, that's a rate problem, like miles per hour. Okay, that's a rate. So it is the actual last one here. It's the rate because they're based on time. So I think the best answer would have been the last one. Okay. Okay, the table above gives you the values of a differentiable function f and g and the derivatives at 1. Perfect. This is exactly at 1. Now, if h of x is equal to this crazy ugly thing, what is the derivative? So we have to just take the derivative. Now, be aware, let me write this a little prettier. H of x is really parentheses 2f of x plus 3 and parentheses 1 plus g of x, okay? Now, because of this stupid parentheses, we know it's multiplying, so we have to use product rule. So when I take the derivative, go back to product rule, derivative of the front, leave the back alone, derivative of the back, leave the front alone. So derivative of the front is, what's the derivative of this guy? It's going to be 2f prime of x plus 3. The derivative of 3 is 0. And we're done. Leave the back alone. And then plus the derivative of the back. The derivative of the back is just g prime. Leave the front alone. Now we have to go back and just copy all these numbers in. F prime is negative 2, so it's 2 times negative 2. 1 plus g at 3 is negative 3. Plus g prime is 4. 2 times 3 plus 3. Okay, so it's because it was the product rule that made this a little bit tricky. Okay, and then we can just figure out the rest of it. This is negative 4. That's a negative 2 plus 4 times 6 plus 3 is 9. We're at 36. I don't need that. 36 plus positive 8. It looks like it's going to be 44. 44 is the answer. Okay, hopefully that was helpful. Now, again, all these problems, I try not to overthink. They tell me to take the derivative. Yes, sir. Yes, ma'am. I'm going to take that derivative. Okay, this problem here, let's go ahead. The function f is differentiable and has a value shown in the table above. Both f and f prime are strictly increasing on the interval between 0 and 5. Okay. Which of the following could be the value of f prime at 3? So f prime is the derivative. So there's a couple of different possibilities here, but let's go ahead and take a look here. So f prime at 3, we're given a bunch of table values. So here's 3. What could the derivative be? We could use the values around it. So we could say 48.05 minus 39.20 over 3.1 minus 2.8. And that would give us a rough slope of what the slope would be at f at 3. Okay, so if I do the math, 48.05 minus 39.20 divided by 0.3. I'm getting the number is 29.5. Okay, so this is one possibility. Let's see, both f and which of these could it possibly be? 29 point. Oops. I lost. What is it? Okay. Now, since that number is not there, there's no guarantee. Okay, so let's try another one. Let's try 31, the 20. Let's try 20, 33.1 and other way around. 48.05 minus 45 over 3.1 minus 3.0. Okay, because 29 and 30 are really darn close to each other. So it could be either of those. Let's go ahead and try these two. 48.05 minus 45 divided by 0.1. And that gave us 30.5. Okay. So from the points I'm looking at, so it could be 29 or it could be 30. Okay. And then let's just look at one more point. Let's go ahead and go the other way. Let's go 45 minus 39.20 over 30 minus 2.8, 3.0 minus 2.8, okay? 45 minus 39.20, and then we're going to divide that by 0.2, and it says 29. So this was 29. Okay, so the problem is when I tried going from 3.1 to 2.8, the answer was 29.5. Now, the mean value theorem says only that number 29.5 is guaranteed. They don't give me 29.5. So I can't use 29.5. So I'm going to go ahead and look at the other two numbers. On the left side, from here to here, it is going to be, we said 29. And then from here to here, it's going to be 30. So since it's increasing, it can't stay at 29. It can't be 29 to 29. And it couldn't have gone up and gone down. So it has to be above 29. And it has to be below 30.1 or 30.5. So it has to be 30, which is caught in between it. Okay. So it couldn't be 30.5 because that's the right side slope, right side most slope. So we can't be from 35 to 35. That doesn't work. On the left side, it can't be 29 to 29. So it has to be between 29 and 30.5. And our choice here was only 30. Okay, that one was a little tricky. Oh shoot, really? Darn it. Thanks, Erica. I'll take a look at it today. Gosh, I even double checked it, but my double check is probably I should triple checked it. Mr. Co. Okay, hopefully that was helpful. For that one, that made sense. And then the next one is if f is differentiable function, okay, f of 3 is 8. F of 3 is 8. Let me insert another page. pen. Okay. If f is a differentiable function such that f of, well, come on. F of 3. Oh, what are you doing? 3 is equal to 8. It's terrible. And the derivative at 3 is 5, okay? Which of the following statements could be false? Okay. Could be false. All right. Could be false. So we know that the derivative exists at 3, so it's differentiable. We don't know it's continuous. So which of these could be false? So, see, the derivative exists. That means it's continuous and differentiable at 3. So, which of these? So the first one is just saying that, let's give it a graph here. That's 8 and this is 3, okay? So the first one is saying that the limit exists from both sides. So is it true that both sides? Well, if it's differentiable, we can say it's continuous. So this should go across like that, okay? And it does exist at that has to be 8. Okay, that's going to be 8. So we're going to say that is true because it's differentiable. And if it's differentiable, it means it's continuous for us. But if it's continuous, doesn't mean it's differentiable, but we can go backwards. Okay, if this is true, that means the left and the right side both agree. So that means the second answer here has to be true also. This guy here is the derivative equation. Is it true that if I plug in f at 3, plug in 3 is 5. If I plug in 3 here, we'll come back to that one. This one here is, oh yeah, these are both the derivatives, right? These are both the definition of a derivative. And they say the derivative is 5 and they're both derivatives 5, okay? And now the question is it true that there's a limit that exists here? And we have no clue about the limit. We have no clue what's going on with f's own graph. So the last one is the one that could be funny. Okay. So it turns out this is the one. Because these are just the definition of a derivative. That's just the definition of a derivative. Okay, Saphir, does that make sense? These two are different. Which one did you think that it might have been?
I put A.
Oh, A? Okay, so what happens when it's differentiable? We know it's continuous there. Because if I draw you a graph, let's see, is this graph, does the derivative exist there? No, right? So the derivative does not exist. And what if I give you a corner here? That derivative does not exist, but the graph is continuous. So since the derivative does exist for us, we can say it's continuous. And if it's continuous, that means there's no breaks in the graph. Okay. That's the reason why. And then, so the first two are actually the same answer. If the limit does exist, that means both left and right side agree, and they both agree to be 8. And this is just another way of saying again, whoops, darn it. This is just another way of saying a derivative in general. And the both derivatives, the derivative does exist, so both these limit equations are true. Okay. All right, any other questions that I can help you guys out with? Haruka, I'm going to go ahead and take a look at the FRQ one more time, okay? And you can go to refresh it, and hopefully it fixes it, okay? Thank you.